Okay, hello everyone. Welcome to the 66th online Spintronics seminar. It's a great pleasure to introduce today's speaker, Professor Takahiro Moriyama. He received his master's degree from Tohoku University. He then flew to the US and joined Professor Zhang Xiao's research group at the University of Delaware, where he and I overlapped 4 years. He's 1 year ahead of me and has been my direct mentor since I joined the group. And someone who just started lab work, I learned a lot from him. For example, not to use a Play-Doh to hold a coaxial cable, but rather should go to machine shop and make a real fixture. At that time, he's one of the two role models in John's lab who has set a very high work ethic standard. He's the one who always work on weekends and till midnight, and if I remember correctly, also around Christmas. That kind of dedication to experiment deeply impressed me till today, and frankly also scared me a lot at that time as a new grad student. Because this was gonna be my life for the next few years. Luckily it was not, because I was lazy. After Taka finished his PhD in 2008, he joined Dr. Dan Roth and Bob Berman's group as a postdoc in Cornell before he moved back to Japan in 2012. He currently holds an associate professor position at Kyoto University. His research expertise is on spintronics, in particular on antiferromagnetic spintronics, part of which will be discussed in his talk today. So without further ado, Taka, please take it from here.
Okay, thank you for the very nice introduction. So I'm Takahiro Moriyama. Can you hear me, Bob? Good? Okay.
Yes.
So I'm Takahiro Moriyama from Kyoto University, Japan. So I really thank the Shin and Kir for giving me this opportunity to present our recent work in this spintronic workshop. Okay, so actually I have joined several online international seminars up to now, and then as an audience and sometimes as a presenter. It is always good to hear the latest research results in those meetings, but the only drawback is that for people living in Japan, those international seminars are always held at a very crazy hour. So, but this time I really appreciate the kind arrangement so that I don't have to get up too early or stay up too late. Okay, so the title of today's talk is Controlling Antiferromagnetic Resonance. Okay, so the outline of today's talk is the following. I will give some brief introduction about the antiferromagnetic resonance. Show our terahertz spectroscopy technique and move on to some typical results of the antiferromagnetic resonance taking a typical antiferromagnetic nickel oxide. And then I will discuss our recent results on controlling the antiferromagnetic resonance frequency by cation doping into the nickel oxide, and as well as the spin pumping effect by using the nickel oxide platinum interface. Okay, so I have to mention this. This work is it's done in collaboration with Gifu University in Japan, UCLA, Yaroslav Selkovniak, and Kyoto University. And I also appreciate the various financial supports written here. So I'm working on the antiferromagnetic spintronics the past years. And antiferromagnetic spintronics is actually now one of the exciting branches of the spintronic fields. So comparing to the ferromagnetic materials conventionally used in the conventional spintronic devices, antiferromagnets have much smaller susceptibility and no stray field, which basically enable us to make a high-dense memory, for instance, shown here. And more interestingly, or most interesting property of the antiferromagnet is its very high resonant frequency, which can go up to terahertz range. So therefore, they are one of the few potential materials which can work at the terahertz frequency. This material could bridge the terahertz technology and the spintronic field. So I'll talk about this part in this presentation. So first, I'd like to briefly explain the what the antiferromagnetic dynamics is. So we start from usual magnetization dynamics in ferromagnet, here, shown here. So we all know that on resonance, the ferromagnetic moment precesses around the effective magnetic field. This equation of motion is basically described like this. So here we should note that the magnetic moments always precess in counterclockwise with respect to the effective field direction. Okay. So if you flip the magnetic moment in the other direction by applying the effective field, by applying the external field or some other technique, you see the counterclockwise precession with respect to the effective field still remains. Okay. Then we just think about the antiferromagnet case, in which the magnetic moments are coupled antiparallel to each other. So as they still need to satisfy the equation of motion for each sublattices, as a precession motion will be like this way. Okay. So here you notice that in the ferromagnetic case, they can precess with keeping the moment parallel to each other. On the other hand, antiferromagnetic moment cannot keep the antiparallel coupling while precessing. So this basically increases system energy by the exchange energy, because antiferromagnetic prefers the antiferromagnetic coupling, okay? But it cannot maintain that during the precession. So this is why the exchange field term comes into the ferromagnetic resonance like this. This exchange field is typically quite large. It can be up to like 1,000 Tesla in some material. If you calculate this, if you estimate this resonant frequency, it can be up to terahertz range. Okay. So in order to detect the antiferromagnetic dynamics, we know that we need to do the experiment in terahertz range, basically. So study of antiferromagnetic resonance is indeed quite old. Back in 1960s, Tinkham, who is famous for superconductivity, was actually doing a frequency domain terahertz spectroscopy using a mercury lamp and diffraction grading. The schematic is shown here. However, the terahertz power at the time was very small, and the sensitivity was not enough for detailed measurement. On the other hand, recent advancements in terahertz technology allow us to do some time domain spectroscopy using a femtosecond laser and the magneto-optical technique shown here. Actually, our terahertz system is a continuous wave frequency domain system. The schematic is shown like this. This system is basically composed of two laser sources with variable wavelengths and two pair of photoconductive switches. So the laser with a slightly different wavelengths or frequency mixed and give an amplitude modulated beam whose frequency is delta F, something like this. So in our particular system, making the wavelength difference 2 nanometers, we get about 1 terahertz beat. So this beat laser drives the photoconductive switch at the delta F frequency. And when we bias this photoconductive switch, we can excite a time-dependent E field in the gap. And this time-dependent E field oscillating at terahertz will emit a terahertz electromagnetic wave, something like this. And usually we have the silicon lens on the back of this photoconducting switch to focus the X ray. So the actual setup is actually quite simple. As you can see in this photo, we have the pair of antenna, emitter and the detector, which are connected through the optical fibers, and then at the end we have the laser source. So we basically place a sample in between these antennas. Sometimes we use a cryostat to vary the temperature of the sample. Okay. So to say that the sample showing here, showing this presentation, are all bulk material made by conventional sintering process. We basically start from the powder material and mix them together and press to pellet shape and fire in the furnace for some time. And then we get something like this, this size pellet. This dimension is like a diameter is 4 millimeter and the thickness is 3 millimeter. Okay. So this is a typical terahertz transmission measurement results for an antiferromagnetic nickel oxide. The vertical axis here is a photocurrent detected by the detector, which is basically proportional to the transmitted terahertz waves through the sample. So you can see very sharp dip right at 1 terahertz. And we basically from this data we obtain the terahertz transmission of the nickel oxide by comparing this raw data with a measurement of the air, basically without the sample. And after processing data, we can see the clear absorption peak at 1 terahertz, which comes from the nickel oxide antiferromagnetic resonance. So in the next slides, I'd like to show how we analyze the resonant peak. So the nickel oxide is basically made of 2 magnetic sublattices. It's a simple collinear antiferromagnet. And these sublattices are coupled anti-parallel to each other, something like this. So each sublattice A and B has an equation of motion resembling the so-called LLG equation. So here alpha is a damping constant, and alpha AA is a damping constant within the sublattice A, and the damping constant AB is the damping constant of sublattice A influenced by the sublattice B. It's a cross term. So these 2 equations coupled by an effective field described basically like this. So for the nickel oxide, it's simple magnetic structure. So assuming the magnetic properties of the sublattice A and B are identical, and we can simplify all these parameters like sublattice magnetization, anisotropy energy, and damping constant, something like this. And we can solve these simultaneous equations and obtain the frequency-dependent susceptibility. Okay. Since we are doing the absorption measurements, for the absorption spectra, we take the imaginary part of the susceptibility. So you can see this is nothing but the Lorentzian function. It's very similar to the ferromagnetic case. We can basically fit this fit the absorption peak with a Lorentzian function to get resonant frequency and the line width. And from the line width also we can derive the damping constant alpha. Okay. And one other important data is the temperature dependence of the resonant frequency. So unlike the ferromagnetic case, antiferromagnetic resonant frequency does not change much by the external field. So it basically doesn't really respond to the external field. but it often sensitivity changes with the temperature, something like this. In the nickel oxide case, the frequency drops rapidly above room temperature toward the near temperature. So this temperature dependence actually also tells us some important parameters. The temperature-dependent parameters in the resonant frequency equation taken from the previous slides can be this magnetization of the sublattice M0 and also the anisotropy energy. So it is a bit difficult to assume that difficult to consider the exact function for this temperature dependence of those two parameters, but considering the anisotropy energy K, it should be a function of M0. The resonant frequency can be generally written in terms of M0 to the power of exponent n, something like this. So this is the usual analysis. So the this temperature dependence of M0 can be derived from the simply Brillouin function. We therefore fit the data with this equation to obtain the say intrinsic resonant frequency, basically the resonant frequency at 0K, as well as this new temperature. So this 1.1 terahertz and the new temperature 523K is very consistent with previous experiments. So this slide shows a comparison of the single crystal and the polycrystalline nickel oxide samples. So as you can see, the resonant frequency and new temperature are almost the same for the single and the polycrystalline cases. But on the other hand, the damping constant is actually significantly higher, larger for the polycrystalline case. So similarly to the ferromagnetic case, this result basically implies that some magnetic or structural inhomogeneity could affect the damping constant. So it is basically say that it's probably the extrinsic contribution to the damping in the antiferromagnetic material as well. So I just want to make a short summary here. So in our system, we can do the high resolution antiferromagnetic resonance measurement in terahertz range. Since it's a high resonance, we can see the line is very well. We can do the line with analysis, and from that we can derive the damping constant alpha. And from the temperature dependence of the resonant frequency, we can also derive the near temperature as well as the intrinsic resonant frequency. For now, this system can change the temperature from 4K to 500K. And for now, we can only take a bulk sample because this measurement is absorption measurement. We need some volume. We are trying to do the thin film measurement, but it's not successful so far. Okay. So from here, I would like to show how we can control the antiferromagnetic resonance. So based on this equation, the resonance equation, if you want to control the resonant frequency, you need to modify basically either the exchange field HEX or the anisotropy field HA. So in order to do that, the easy way is to dope some cation into nickel oxide to modify the exchange or anisotropy. So in this particular study, we doped the manganese, lithium, and the magnesium cations into nickel oxide and then see how the resonance is controlled. So here, the magnesium doping is considered the magnetic doping. The lithium doping is actually Hall doping, which narrows the band gap of the nickel oxide. And the magnesium cation is basically enlarging the band gap of the nickel oxide. Okay. So in this slide, the upper panel shows the temperature dependence of resonance frequency for various doping concentration from which we can characterize the new temperature as well as the intrinsic resonance frequency, omega 0. Then the lower panel shows the XRD pattern, which ensures that the doped cations are substituting the nickel cation site while keeping the basic nickel oxide crystalline structure. Well, except for the manganese 10% doping case, which gives basically different behavior in the resonance frequency as well. So we have the for the 10% manganese, we have some impurity peaks, which is different from the nickel oxide structure. So, but overall, as you can see, the resonance frequency basically goes down by the doping, regardless of the cation element. So here, the slide summarizes obtained intrinsic resonance frequency and the new temperature for various doping element as a function of doping concentration. So here we assume the new temperature is basically proportional to the exchange field. We have this quadratic relation between the omega 0 and new temperature like this. So based on this relationship, comparing the omega 0 and the Tn reduction for each doping concentration, we can say that from this data, the dominant effect of the manganese doping, which is a magnetic doping, is a reduction of the HA. And for the Mg doping, the dominant effect is seem to be reducing the exchange field. And lithium is, we don't have much conclusion with because new temperature and omega 0 do not change much. So the line width and or the Q factor can also be modified by the cation doping. Comparing to the Mg and the lithium magnetic non-magnetic doping, the manganese doping, which is magnetic doping, seem to increase the line width and decreasing the Q factor significantly here, which might be related to the increase of magnetic inhomogeneity due to the doping of this magnetic cation. So very recently, we also investigate doping effects on alpha hematite, in which one can excite the antiferromagnetic resonance as well. This material is actually not a full antiferromagnetic material, but it is a weak ferrimagnetic material. It has some small spontaneous magnetization due to the DMI effect. But we can also access to the antiferromagnetic dynamics in this material. So, and also this material has a very strong temperature dependence of the resonance frequency, as you can see here. It changes quite a lot from in this temperature range. This is basically associated with so-called Morin transition, to which the spin orientation changes by the strong temperature dependence of magnetic anisotropy energy. So in this material, we find that when we dope with aluminum, ruthenium, rhodium, and indium, this actually can dramatically modify the resonance frequency, something like this. And it is a bit busy graph, but if we compare the resonance frequency at the room temperature, say here, by the cation doping, we can basically cover the resonance frequency from millimeter wave range to the terahertz wave frequency range. So this might be good for like a future telecommunication technology, like 5G, 6G. Okay. Okay. So from this, from here, we also want to discuss the discuss the spin pumping effect in the antiferromagnetic dynamics. So this is another effect which influences the magnetic resonance. This is we call the spin pumping effect. So this effect is an effect that spin dynamics can create and pump the spin current to an adjacent material. So this spin pumping effect is widely examined in ferromagnetic dynamics, but not for antiferromagnetic dynamics. So here we examine the spin pumping effect in the nickel oxide platinum structure. So the sample used here is a nickel oxide platinum granular system where platinum granules dispersed in the nickel oxide matrix. So this is also made by the sintering process. We just starting from mixing a platinum powder and the nickel oxide powder, and then press them together and fire it and make a bulk pellet. So the detailed schematic of the spin pumping diagram is shown here. Basically, the nickel oxide dynamics would pump the spin current into the platinum granule. Yeah. The spin current will be dissipated due to the spin orbit interaction in platinum, which basically results in the loss of spin angular momentum in the system. So therefore, if we measure the damping constant, we should observe the enhancement of damping constant described by this equation, where G up down is the so-called spin mixing conductance. This is a parameter which characterizes the spin pumping effect. And the S is nickel oxide platinum interface area, and the V is the volume of the nickel oxide. So, by increasing G up down or this interface area S, we should observe the increase of the damping constant. So this is a structural analysis of this nickel oxide platinum granular samples. From the XRD data and the optical microscope image shown here, we can see that platinum granule and the nickel oxide matrix are well segregated. There are no intermixing between these two materials, and we seem to have a clear interface of the platinum nickel oxide. And also the temperature dependence of the resonant frequency is almost the same, regardless of platinum composition, basically, which basically indicates that the magnetic properties of the nickel oxide are invariant, even with the introduction of the platinum granule. So platinum granule does not influence the resonant property in the nickel oxide. So this is basically the central results of this experiment. It's a line width as a function of platinum composition. So as you can see, as we increase the platinum composition, we increase the surface area S, the interface area S. We see the increase of line width. Therefore, the damping constant also increases. So as a control sample, we also measure the sample with air holes instead of platinum granules, and see how the damping see the damping does not change much in this case. So we therefore can conclude that the platinum nickel oxide interface is basically responsible for this damping enhancement. Here. We estimate the spin mixing conductance G up down, which characterize the spin pumping effect, using the basically granular size and the shapes taken by the microscopy images shown in 2 slides ago. We quantitatively estimate for the first time in the mixing conductance to be 12 per nanometer squared, which actually turns out to be comparable to the ferromagnetic case. For instance, this value is very similar to permalloy platinum interface. Okay. So here, I'd like to summarize all the presentation today. So we discussed the antiferromagnetic resonance and our terahertz spectroscopy technique with experimental result, with a typical experimental results for nickel oxide. From our recent work, I showed a quantitative estimation of the spin pumping effect in platinum nickel oxide interface. And I also discussed how we can control the antiferromagnetic resonance by cation doping into the nickel oxide as well as the alpha hematite. Those might be useful for future terahertz technologies, such as, say, terahertz absorbers and also filters. And finally, I also recommend you to check out our recent publication about this magnetics roadmap, which include antiferromagnetic magnetics. Okay. For that, thank you for your attention.
Thank you very much for the interesting talk. This talk is open for questions. If you have questions, please use the raise hand function at Zoom. Or you can send me a private message. And if you are watching this on Twitch, you can type your question in the chat box and I'll read it for you. Do we have any question? I can ask Ren, please go ahead with the question.
Hello, hi. Thanks for the really nice talk. So I just want to make sure that in the spin pumping from nickel oxide, did you apply a magnetic field to the sample, or magnetic field is not required?
No, we didn't apply the external magnetic field. This is the zero field measurement.
Okay. So for the zero field, my understanding is that the coherence mode of nickel oxide in the absence of magnetic field. So the neo vector basically undergoes a linear polarization. So I'm not quite sure why a linearly polarized neo vector can result in a finite spin pumping. Maybe I have missed some point here.
Well, this is an absorption measurement. We are not really detecting the spin current to actually, like, say, using the inverse spin Hall effect or some kind of things.
Oh, I see. Okay.
Measuring the absorption. So maybe the linearly polarized this spin can be decomposed into like a circular polarization. I think.
I see. Okay, so
those are absorbed by the platinum. I see that. Well, that's our interpretation.
Oh, I see. Okay. So the enhanced damping. So that is applicable for, regardless of the polarization status. But just,
right.
Okay.
And of course, if I want to measure this inverse spin Hall effect or some kind of voltage measurement, this configuration doesn't really give the voltage, I guess. Well, you know well. Yeah.
Oh, thanks very much. Thanks for clarification.
Yes.
Thank you. Do you have other questions? I want to ask one quick question. One of the potential applications for this is as a terahertz absorber. But if you want to use this as an absorber, you don't want it to be absorbing at all the frequency spectrum. But from your experiment, looks like comparing with just air, there is a very large broadband loss for terahertz between 100 gigahertz and a couple of terahertz. Where does that broadband loss come from?
The one thing is that this nickel oxide is not really the good insulating material. The band gap is it's not so wide. So there's I think the reflection, not the absorption, but there's a reflection from the sample. That's why we have a small reducing transmission here. But this is not this part is not absorption. It's simply the reflection.
I see. I see. Yeah. Yeah.
And for the absorber, I think what's important is this ratio, like this background to the absorption. In this case, we only have right now we have I guess 90% absorption, which I don't know if it's sufficient for practical application or not. But we can also study in this direction to increase the absorption.
I see. And at this moment, you've already demonstrated when you dope it with the different materials, you can actually continuously tune this over a pretty wide range, right? Thank you. Still want to